Consider this. Everything you do on a computer, a tablet, or a phone, watching a video of a cat playing a piano, sending a message to a friend across the planet, boils down to something incredibly simple. A long string of ones and zeros. That's it. It's a language called binary. Think of it like a light switch. When the switch is on, it represents a 1. When it's off, it represents a 0. Every single letter you type, every color on your screen, every note of music you hear, is just a unique combination of these on and off signals. It's a beautifully simple system that has powered our digital world for decades. This binary system is the fundamental building block of what we call classical computing. It's the kind of computing we all use every single day. Your laptop is a master at flipping these switches on and off at incredible speeds. It can perform billions of calculations per second, all by manipulating these simple states of on or off. This concept is so powerful because it's reliable and easy to control. A 1 is always a 1 and a 0 is always a 0, my son. There is no in between. This black and white yes or no logic has allowed us to build everything from pocket calculators to the vast interconnected network we call the Internet. So what are these magical switches that power our digital lives? They're called transistors. A transistor is a microscopic semiconductor device that can act as an amplifier, or it can act as a switch. For computing, we are most interested in its role as a switch. Think of it as the world's tiniest, fastest light switch, controlled by an electrical signal. When a small electrical current is applied, the transistor turns on, allowing a larger current to flow through. This on state is R1. When the small controlling current is removed, the transistor turns off, stopping the flow. That's R0. Your computer's brain, the central processing unit or CPU, contains billions of these transistors. These transistors are the workhorses of classical computing. They are arranged in complex circuits called logic gates. AND gate outputs 1 only if both inputs are 1. Or gate outputs 1 if at least one input is 1. NOT gate inverts the input. By combining these gates, computers can perform complex arithmetic. They can make decisions, they can store information. Every time you click your mouse, your computer sends signals that flip millions of these transistors. It's a symphony of electricity, conducted at incredible speed, all happening inside a small silicon chip. The sheer number of transistors we can pack into a small space is what makes modern computers so powerful. Just when it seemed like we were hitting a wall, science presented a new, mind-bending path forward. Instead of fighting against the strange rules of the quantum world, what if we embraced them? What if we could build a computer that uses those bizarre behaviors, like electrons tunneling through walls, to its advantage? This is the core idea behind quantum computing. It's not just a faster version of the computers we have today. It's a fundamentally different way of processing information. It's a leap into a new computational dimension, one that operates on the very laws of physics that govern atoms and particles. It's a whole new ballgame, and the rules are wonderfully weird. Think of it this way: a classical computer is like a regular light switch. It can be on or it can be off. It's a binary choice. It solves problems by trying every combination one after another very quickly. But a quantum computer is more like a dimmer switch. It can be on, off, or somewhere in between. In fact, it can be on and off at the same time. Let's dive a little deeper into the star of the quantum show, the qubit. As we said, a classical bit is simple. It's a 0 or a 1. Illustration comparing a classical bit next to a quantum bit. It's like a coin lying on a table. It can either be heads up or tails up. You can look at it and you know its state with absolute certainty. This is the foundation of all the digital technology we use today. A qubit is not like a coin lying flat on a table. Instead, imagine a coin that is spinning in the air. While it's spinning, is it heads or tails? Well, it's kind of both and also neither all at the same time. It has a certain probability of landing on heads and a certain probability of landing on tails, but until it actually lands and you measure it, it exists in a state of all possibilities. This is what a qubit is like. It can be a 0, a 1, or a blend of both simultaneously. This in-between state is the first piece of quantum magic we need to understand. This ability to be in multiple states at once is a property called superposition. Before it is measured, a qubit exists in a coherent superposition of both 0 and 1. It's not 50% 0 and 50% 1 in the way you might think. It is literally both at the same time. When you finally measure the qubit, which is like stopping the spinning coin to see how it landed, it will collapse into a definite state of either 0 or 1. Let's talk more about this amazing idea of superposition. It's one of the cornerstones of quantum mechanics and what gives quantum computing its power. The spinning coin analogy is a good start, but let's try another one. Imagine you're in a maze. A classical computer would solve this maze like you or I would. It would try one path, hit a dead end, go back, try another path. It would keep doing this one path at a time until it found the exit. This can take a very long time, especially if the maze is large and complicated. It's a methodical but slow process of elimination. Now imagine a quantum computer solving that same maze. Instead of a single person walking the paths, a quantum computer is like a flood of water. When it reaches a fork in the path, it doesn't have to choose left or right, it can do both. The water can flow down every single path in the maze simultaneously. Some paths will lead to dead ends, but the parts of the water that went down the correct paths will continue on. In a very short amount of time, the water will have explored every possible route, and the first drops to emerge will reveal the shortest path to the exit. This ability to explore all possibilities at once is a direct result of superposition. This all-at-once capability is what makes quantum computers so different. A classical computer operates sequentially, performing one calculation after another. Even with multiple processors, it's still a limited number of parallel tasks. A quantum computer, on the other hand, operates in a truly parallel way. If you thought superposition was strange, get ready for its even weirder cousin, quantum entanglement. Albert Einstein famously called this phenomenon spooky action at a distance, and for good reason. Entanglement is a special connection that can exist between two qubits and between more qubits. When qubits become entangled, their fates are linked, no matter how far apart they are. What happens to one instantly affects the other, even if they are on opposite sides of the universe. It's a connection that seems to defy our classical understanding of space and time. It's one of the deepest and most mysterious aspects of the quantum world. Let's use an analogy. Imagine you have a pair of magic gloves. You put one glove in a box and the other in a second box. You don't know which is the left glove and which is the right. You then mail one box to your friend in another country. The moment your friend opens their box and sees they have the left glove, you instantly know without even looking that you have the right glove. That seems logical, but with quantum entanglement it's much stranger. It's as if neither glove was left or right until one was observed. The gloves existed in a state of being both and neither. The act of observing one glove instantly forced the other to become its opposite. This is what happens with entangled qubits. For all its magical feeling, it is absolutely crucial to remember that quantum computing is not magic. It is science. It is the result of over a century of rigorous experimentation, brilliant theoretical work, painstaking engineering. Every single spooky or weird aspect of quantum mechanics has been tested and verified in laboratories around the world, time and time again. The predictions made by the theory of quantum mechanics are among the most accurate and precisely tested predictions in the entire history of science. This isn't wishful thinking. It's based on observable, repeatable evidence about how our universe works at its most fundamental level. The journey to building a quantum computer is a story of incredible scientific and engineering challenges. Qubits are extremely fragile. The slightest disturbance from the outside world, tiny vibrations, stray magnetic field change in temperature, can destroy their delicate quantum state of superposition. This is a phenomenon called decoherence. It's like the spinning coin being knocked by a gust of wind, forcing it to land prematurely. To prevent this, scientists have to build incredibly controlled environments to house these quantum processors. They are often cooled to temperatures colder than deep space, just fractions of a degree above absolute zero, and shielded from all external interference. Building the hardware is only half the battle. We also need to develop the software, the quantum algorithms, to run on these machines. They are not wizards chanting spells. They are scientists and engineers manipulating atoms with lasers, magnetic fields, microwave pulses. So, what's the big deal? Why are governments and companies investing billions to build these incredibly complex machines? Quantum computers can solve some of the world's most intractable problems and revolutionize entire industries. Let's start with medicine and materials. Designing new drugs and materials involves understanding the quantum behavior of molecules. Quantum computers can simulate these molecules with far greater accuracy than classical computers. This could lead to new life-saving drugs, new catalysts for clean energy, new materials like room-temperature superconductors. Another huge area is cryptography, secure communication. Encryption protects our bank accounts, encryption protects government secrets, encryption protects online messages. A powerful quantum computer using Shor's algorithm could break this encryption. That's a threat, but it also pushes a new era of quantum-safe cryptography. Consider complex optimization problems. These require finding the best solution from an enormous number of possibilities. Optimizing shipping routes to save fuel, designing more efficient financial models, improving machine learning, improving artificial intelligence. Quantum computers can explore many possibilities at once and find optimal solutions currently out of reach. This could massively impact logistics, finance, scientific research. We are still in the early days of the quantum era. By harnessing the weird rules of the quantum realm, we're on the verge of unlocking a new level of computational power that will change our world. Consider it.